So far, we have talked about networks as whole things and 802.1.12 devices connected together. A local area network humming along. But when you send a single message across a network, something remarkable happens under the surface. That message is handled by not one system but 7, each doing its own small job, one after another, in a strict order. This is the OSI model and 802.12, the Open Systems Interconnection model and 802.12.5, and it is the single most important mental framework in all of networking. It is a map, drawn once and agreed by the whole world, that says, here is how a message travels from the app on your screen, all the way down to the raw signal on a wire, and back up again on the other side. Once you hold this map in your head, every networking topic you ever meet will have a clear place to live. So let us learn the 7 layers. Here is what we will understand today. First, why we bother splitting networking into layers at all. Second, the 7 layers as a whole, so you see the shape before the detail. Third, the 2 lowest layers, physical and data link. Fourth, the middle layers, network and transport, where a lot of the real action lives. Fifth, the 3 top layers that sit closest to you. And sixth, encapsulation and 802.12, the elegant idea of how your data actually moves down through all 7 and back up. Let us begin. Let us start with the question a good engineer always asks. First, an 802.100 will do. Not, what are the layers, but why layers at all? The reason is that networking is an enormous problem. Getting a message from one program to another might involve a Wi-Fi radio, a copper cable, a router in another country, and an app written by a stranger and 802.112, all cooperating perfectly. If you tried to design all of that as one giant tangled system, nobody could build it, understand it, or fix it. So we do the thing engineers always do with a huge problem. We cut it into layers and we give each layer exactly one job. One layer worries only about the physical signal. Another worries only about finding a route. Another worries only about reliability. And crucially, each layer trusts the layer below it to do its job and offers a clean service to the layer above. The payoff is independence. Because the layers are separated by clear boundaries, you can completely change one without touching the others. Swap a copper cable for fiber and 802.12, only the bottom layer notices. Invent a brand new app and 802.1.2 ours. The layers underneath do not care. This is the same reason we build with standard bricks, agree on the joints, and everyone can build freely. So the takeaway, the OSI model splits networking into 7 layers, each with a single job, so that each layer can be built, understood, and swapped on its own 802.12 veil. That separation is the whole point. Before we go layer by layer, let us see the whole stack at a glance. Group into 3 natural tiers because the shape is easier to remember than 7 separate names. At the top sit layer 7, 6, and 5, and 802.12, the application tier. This is what your programs actually speak, the language of browsers, email, video apps. It is closest to the human. In the middle, alone, sits layer 4, transport. Its job is reliable delivery from one end all the way to the other and 802.12, making sure the whole message arrives correctly at the far program. It is the bridge between the apps above and the network below. And at the bottom sit layers 3, 2, and 1, and 802.112, the network tier. These do the physical heavy lifting, finding a route, hopping device to device, and pushing the actual bits down a wire, closest to the machine. So the takeaway, read the stack top to bottom and 802.12. The upper layers are what apps speak. Transport carries the message end to end, and the lower layers move the raw bits across wires and routers. Hold those 3 tiers, and the 7 names slot right in. Now let us walk up from the very bottom, starting with the 2 lowest layers, which work as a close pair. Layer 1 is the physical layer, and it is exactly what it sounds like, the actual signal. It does not know or care what your data means. Its only job is to turn ones and zeros into something that can travel an 802.1.2, a voltage on a copper wire, a pulse of light in a fiber, a radio wave in the air, an 802.1.2, and to turn it back into ones and zeros at the far end. cables, connectors, radio frequencies. That is all layer 1. Layer 2 is the data link layer, and it gives those raw bits some structure. It packages them into neat bundles called frames, and it handles delivery between two devices that share the same local link and 802.812, your laptop to your Wi-Fi router, say. To do that, it uses hardware addresses, called MAC addresses, that are burned into every network card. Layer 2 says, deliver this frame to that specific device right next to me. Notice the boundary between them. Layer 1 is dumb and physical. It just moves signal. Layer 2 adds just enough intelligence to say who, locally, the frame is for. Together, they get data reliably from one device to the very next one on the same network and 82-fold, but no further. So the takeaway, layer 1 moves raw bits as a physical signal, and layer 2 wraps those bits into frames addressed to the next device on the local link. That is local delivery handled and 802.12. Now we need to go further. Layer 2 can only reach the device next door on the same local network. But the whole point of the internet is reaching a machine on the other side of the planet. That leap is the job of layer 3 and 802.12, the network layer. Layer 3 wraps your data into units called packets, and it introduces the address that makes the global internet possible, and 802.12, the IP address. Unlike a MAC address, which only means something locally, an IP address is a logical address that identifies a device anywhere in the world. And it is structured so that the network can reason about where it is. And this is the layer where routers live and do their work. A router reads the destination IP address on a packet and decides which way to forward it, and 802.12 hop by hop, network by network, and 802.12 until the packet reaches its destination. Your packet might cross a dozen routers and several countries, and at each one, it is layer 3 logic choosing the next step. This is literally how a message crosses the world. So the contrast to hold on to. Layer 2 frames stop at the edge of the local link, but layer 3 packets carrying IP addresses can be routed across network after network to anywhere on Earth. Layer 3 is where the network becomes the internet. So the takeaway, layer 3 adds IP addresses and packets, and this is exactly what lets routers forward your data across many separate networks to reach any device, anywhere. Now we reach layer 4, the transport layer, and this is where a genuinely important choice appears, and ATI to Paul. A choice you will meet again and again as an engineer. Layer 3 can get a packet across the world, but it makes no promises. Packets can arrive out of order or get lost entirely. Layer 4 is responsible for turning that best effort delivery into something an application can actually rely on, and 802.12 or deliberately not. The first option is TCP, the Transmission Control Protocol. TCP is the careful one. It checks that every piece of your message arrived, it resends anything that got lost, and it puts everything back in the correct order before handing it up. It is reliable, and that reliability is why it powers the web, file downloads, and email, and 802.12. Anywhere a single missing byte would ruin things. The second option is UDP, the User Datagram Protocol. UDP is the fast one. It just fires the data off and does not wait around to confirm anything. And 802.12, no checking, no resending, no reordering. That sounds careless, but it is exactly right when speed matters more than perfection. A live video call, an online game, a voice stream. If one frame of video is lost, you do not want the whole call to freeze while it is resent, and 802.12. You want to keep going. So here is the rule of thumb to carry away. Reach for TCP when correctness matters, the web and files and email. Reach for UDP when speed matters, calls and games and live video. So the takeaway, layer 4 delivers end-to-end, and you choose its style, and 84 TCP when correctness matters, because it guarantees every byte in order. UDP when speed matters, because it skips the guarantees to avoid delay. Web and files lean on TCP, calls, games, and video lean on UDP. Above transport sit the final 3 layers and 82 wall, 5, 6 and 7 and 82 wall, the ones closest to you, the human. In practice, they often blur together, but each has a distinct job worth knowing. Layer 5 is the session layer. Its job is to open, manage, and cleanly close the ongoing conversation between two programs and A212, setting up the dialogue, keeping track of it while it runs, and tearing it down when it is done. Think of it as managing the call, not the content. Layer 6 is the presentation layer, and it is about format. It makes sure data is in a form both sides understand and AT-hand to want to, handling things like encryption so the data is private, compression so it is smaller, and character encoding so text comes out right. It is the translator and the sealer of the envelope. Layer 7 is the application layer and AT112, and this is the one you actually touch. It is not the app itself, but the networking rules the app speaks, the protocol behind your web browser, your email client, your file transfer. When you type a web address, you are handing work to layer 7. So the takeaway, the top 3 layers set up the conversation, format and secure the data, and present it to the application you use, and A12, session, presentation, and application, working closest to the human. We have all 7 layers now, but how does a real message actually travel through them? This is the most beautiful idea in the model, and it is called encapsulation. It starts at the top with your data and A212, the actual message, say the text of an email you are sending. That is what you care about. Everything else is machinery. Now the message travels down the stack, and here is the key move. At each layer, that layer wraps the data in its own header and AT-SASCII, PUHAND, AT-SASP, a small label carrying the information that layer needs. Transport adds a header saying which program it is for. Network adds a header with the IP addresses. Data link adds a header with the local hardware address. Each layer wraps what it received from above, like putting a letter in an envelope, then that envelope in a bigger envelope, then that in a package. By the time it reaches the bottom, it is a stream of bits ready to go on the wire N8024, and on the receiving machine, the whole process runs in reverse. Each layer peels off its own header, reads it, and passes the rest upward until the original message emerges at the top, clean, for the receiving app. Wrapped going down, unwrapped going up. So the takeaway, as data moves down the stack, every layer adds its own header and AT-SECOND-2L. That is encapsulation and AT-SECOND-2L. And the receiver peels each header off on the way up, so the exact original message arrives at the top. 7 layers in the right order is a lot to hold. So networkers have always used a simple memory trick, and it is worth learning right now so the order sticks for good. The classic mnemonic from layer 1 up to layer 7 is, please do not throw sausage pizza away. Take the first letter of each word and it spells out the layers in order from the bottom. Please is physical, do is data link, not is network, throw is transport, sausage is session, pizza is presentation, and away is application. The 1 is physical at the bottom, 7 is application at the top. Silly sentences stick in the mind far better than dry lists and A212. That is exactly why this one has survived for decades and is still the first thing many engineers recall. Say it a few times and you will never lose the order. So the takeaway, a single silly sentence and AT-112, please do not throw sausage pizza away, and AT-112 runs you from layer 1, physical, all the way up to layer 7, application, in the correct order. Before we finish, let us make sure you know why this model earns its place as the foundation of the whole subject and 812 house. Because it is not just an academic diagram, it is a tool you will use constantly. First, it is a shared language, because vendors all over the world agree on these layers. A network card from one company, a router from another, and an app from a third all fit together perfectly, and A212. They all speak layer 3, they all speak layer 4, without a common map. None of that interoperability would exist. Second, it gives you the freedom to change one layer without disturbing the rest. upgrade your physical connection from copper to fiber, and only layer 1 is affected. Write a brand new application, and the layers below carry it just the same. Each layer is a sealed box with a clean interface. And third, and 82.1. The one you will feel every day, and 82.1. It turns troubleshooting into an orderly checklist. When something breaks, you go layer by layer. Is the cable plugged in and getting signal? Layer 1. Does the device have a valid IP and can it reach the router? Layer 3. Is the application itself responding? Layer 7. Instead of panicking at the network is down, you work up the stack until you find the broken layer. So the takeaway, the OSI model gives the world a shared language, lets any single layer change on its own, and turns a vague, it's broken, into a calm, layer-by-layer diagnosis. That is why it is worth knowing cold. Let us gather the whole class in one breath. Layers split networking into 7 single job parts that stack cleanly on top of one another. Physical and data link move raw bits and frame them for delivery on the local link. The network layer, layer 3, adds IP addresses and packets so routers can cross many networks. The transport layer, layer 4, gives you TCP for reliable delivery and UDP for fast delivery. Session, presentation, and application setup, format and present the data to your program. And encapsulation means each layer adds a header going down, peeled off going up. Next class, and 82112, the TCP/IP model, and how it maps onto these 7 layers, one idea at a time. That is the OSI model, and 8212, 7 layers, one journey, from the app in your hand, down to a signal on a wire, and all the way back up on the other side. It is the map every networker carries in their head. And from here on, whenever we study a protocol or chase a fault, we will point to a layer and say it lives here. Learn the map once, and the whole of networking gets simpler. We will see you in the next class.